All right, guys, let's get started. So today is our great pleasure to host Dr. Zhongshu Gu from IBM TJ Watson Research Center. Zhongshu was actually my mentor when I interned at IBM almost 10 years ago. So we collaborated a bunch of research projects since 2016. And actually my experience or my research collaboration with Zhongshu shaped my research since I was an assistant professor. I am an assistant professor here. So yeah, so he is a staff research scientist at IBM Research. He got his PhD from Purdue University. His research focuses on cybersecurity, system security, security analytics, cyber forensic. So he has published tons of papers in CCS, SNP, NDSS, using security, and has won several best paper awards and multiple other recognitions. So today he will talk about confidential computing foundation application and research. So without further ado, let's welcome Zhongshu.
Hi, hello everyone. Thank you for coming to the talk. So it is my pleasure to come into University of Delaware. So today I'm going to talk about confidential computing. This is also the field that I've been working on in the past 8 years. So here is roughly the agenda for today's talk. So first we will go through the foundation technologies for confidential computing. And then we will talk about how can we leverage confidential computing for different application scenarios. And then in the last part, I will talk about these, what's the current limitations of confidential computing and what's the security challenges of it, and how we do our research to tackle these problems. So in the first part of it, it's about the foundation of confidential computing. You see, I put a AI-generated picture here. It's like a safe box, like a floating in the cloud, and there's a lightning around this safe box. So this is like a vivid analogies to what is a confidential computing tries to achieve. So here, confidential computing tend to protect the workload in a trusted execution environment. And this a trust execution environment can run on the resources, compute resources provided by this untrusted a compute provider. And what attackers perspective say, they want to breach into your safe box to observe what's the computation inside, what's the data running inside this safe box. And they also want to tamper with execution inside this safe box. Okay. So first we will talk about what's data protection mechanisms to protect the data in different stages. And then we'll talk about what's timelines for existing confidential computing technologies. And then we'll talk about the a threat model for confidential computing and what's the security principles that you.
Okay, yeah,
yeah. Then both of them can see the same screen. Okay. Okay, so this is a picture for what's a data protection mechanisms and how it evolved. So first we want, in the first stage, we want to protect the data that in your disk, and then we call it a data at rest. So from the attacker's perspective, they want to gain this unauthorized access to your disk volume, and they can just simply grab your a laptop and to dump your data from your disk. And the simple mitigation for this one, or common a security practice is we can use this disk encryption, right? We can in Linux we have Lux, and in Microsoft Windows we have BitLocker. So it will just encrypt all the data on your disk. If someone gain access to your disk storage, they can only see this encrypted data. Okay. For the second stage, we call it data in transit. It means when you want to transmit the data from one node to another node, and then you need to encrypt this data from one node and transmit it through the network and to the second node. And for the attacker, they can eavesdrop, modify or replay this network traffic. And so the common security practice is to use this secure communications, right? So for example, using the TLS, for two nodes, you can use Diffie-Hellman key exchange to negotiate a session key and use these session keys to encrypt the data between these two nodes. And we see like for both like data at rest and the data in transit, like both of them have these keys or these these TLS keys, but all these keys will be loaded into your main memory. Okay, so the third stage is like how can we protect the data loaded into the system memory, right? So for these attackers, they can just do this snooping on this memory to dump your memory out or to tamper the executions at runtime. And they can also launch this code boot attack, means they can reset your computer and code boot it again and extract the content from your memory. So we call it how to protect the data that is in use. And the invention of confidential computing is to protect such data in use. So here I will talk about the timelines for confidential computing. So here I just want to give a disclaimer here. So this talk will only focus on confidential computing with Intel or AMD's confidential computing technology on its CPUs and NVIDIA confidential computing on the GPU. But just due to my personal research scope, I work on these platforms. But the confidential computing also exists on other platforms. Like IBM, a lot of my colleagues work on IBM's PEF, on IBM's Power architecture. And SC is IBM's confidential computing on IBM Z. And ARM also has a confidential computing technology called the CCA. And the RISC-V, they have this called a COVE. So every platform has their own a confidential computing solutions. But for us, for this talk, I only focus on this Intel, AMD, and NVIDIA solution. So confidential computing first appeared in Intel's platform in 2015. It's called the Intel SGX. SGX stands for a software guard extensions. So it's a process based a confidential computing approach, and appeared in the Skylake architecture of Intel cores. And so the basic idea is say you have your application and you define which part is a sensitive code, which part contains sensitive code, which part contains sensitive data. And then you can refactor your applications and to recompile it and to load some libraries, share the libraries into a trust execution environment called enclave. And inside this enclave, this memory is encrypted. And also they provided integrity protections for the computation inside this enclave. And they also provide another mechanism called the remote attestation. Means you can generate attestation report for this CPU and then send it to Intel to verify whether this is a genuine a CPU confidential computing or not. So if it's not a genuine one, and then they can say, yeah, it's not a genuine one, and then it will not release the keys to run inside of this confidential computing environment. And AMD provide a different line of solution called SEV. SEV here stands for Secure Encrypted Virtualization. So it means this is a virtualization solution. So instead of just protect the enclave inside a process, so it protects the whole VM. So the whole VM's memory will be encrypted. Okay, and it appeared in the AMD's EPYC, this server a processor. So in the first generation of AMD SEV, it only protects the VM's virtual machine's memory with encryption. But you see, when we do this transition of VM, schedule from one VM to another VM, or when we schedule the time for these VMs, and all these CPU register need to dump out and then to reload into your VM state, right? And in the first generation, it doesn't protect this CPU register state. So in 2017, they launched another technique called the AMD SEV ES. ES stands for encrypted states, right? And then this one is to protect the CPU registers during the the VM transition. And for SEV and SEV-ES, they only protect the confidentiality of the memory and the CPU register, but they do not protect the integrity of this VM memory. So in 2020, and then they launched a technique called AMD SEV SMP. This stands for Secure Nested Paging. And then they use this ones to add this integrity protections for the VM's memory. So this is the AMD solution, and we see like in 2021, like Intel switched gear, and they also provided something very similar to like AMD. So this one is called a TDX. It's a trusted domain like extension. So this one is also VM based. It is on the Sapphire Rapids of Xeon's server processors in Intel. And this is very similar to the SEV SMP. So it can provide this confidentiality and integrity protections for the VM's memory. And we see like Intel also discontinued the SGX on its like a desktop like a processor. So it only supports SGX on the Xeon like from like 2021. And we see we are now in an era of AI computation. So we need to offload the computation from like a CPU to GPU, right? So we see like what can be protected on the GPU. And so NVIDIA has this solution called the GPU confidential computing in 2022. And it is on the NVIDIA H100. It's a Hopper architecture. So it can do this memory protections. It's kind of, it does not do this memory encryption, but it do this memory access control on the GPU's memory. And then for the CPUs, it cannot directly access this GPU memory anymore. And then it provides this protected PCIe interface. And then they use bounce buffers to transfer the data from your CPU's system memories to the GPU's memory. And also they provide a mechanism called device attestation. Means when you have your GPU like a plug in to pass through to your VM, and then you can verify so whether it's a genuine NVIDIA GPU or not. So if it's not a genuine one, you do not need to like trust the NVIDIA GPU. And in 2023, like for Intel and AMD, both of them launched a technique called trusted IO. So Intel has a one called like a TDX Connect, and AMD has a one called a SEV TIO. So for this traditional like IO device, if it works with the confidential VM, it cannot read this private memory of confidential VM because this private memory is encrypted, right? So for these ones, for this trusted IO, so they allow you do this device attestation for these IO devices, and then they can allow you to access this private memory directly use a DMA. So it can like increase like the performance a lot. And also for NVIDIA, like for this Blackwell architecture, they announced they will have a new version of confidential computing on GPU. And this one will have this trusted IO support. And then they will also support like a multi-GPU with NVLink encryption. Means like you can pass through like multiple GPUs into your confidential VM. And the NVLink or NVSwitch like connect these GPUs will also encrypt it. So if you have some like powerful attackers that interpose on this NVLink, they can only see this encrypted traffic on it. So this is a general timeline for confidential computing. So we see I put every technique I put a year there. You see like for NVIDIA, like Blackwell GPU, it's in 2024. But most of them, like we see for this confidential computing, it takes years to make it mature. So this year is only the starting date, like this when we see the white paper, read the white paper of this technology. But it usually takes several years for like all the ecosystem get mature. You need the Linux kernel support, host OS, guest OS support to upstream all these like these patches. So it usually like take 2 or 3 years after you can like play with the system in your lab. So here I give like a general picture. So this is a kind of like a VM-based confidential computing. You see this confidential VM here, and one is a malicious VM. And this confidential VM is running on top of like a hypervisor. So they provided by, say, any third party like a compute provider. And the confidential VM has its own memory. This memory connected to the CPU. And it also has this like a shared memory. The shared memory will connect to these IO devices, like a disk. You have this network card. You can also have this like a GPU on it. So we assume like we can have multiple types of malicious attacker. So the first one we consider is a malicious insider attacker. Means this one is, say, the system administrator of your cloud provider. So all these privileged software in the cloud, like they can control the hypervisor, they can control the like a host OS. So they can control all these compute resources, right? So, but from the perspective, like IBM is a cloud provider, so we do not like this concept of like insider attack. So we say like when you run something on the cloud, that means you need to you don't need to fully trust, but you have somewhat like a trust on the cloud provider. But the second type of these attackers, they call external intruder. Means like your cloud, you may be like penetrated by some like external attackers. When they penetrate into your system, and then they can compromise this like a hypervisor control plane, and then they can attack the VMs on your system, right? And then they can also control these neighboring tenants. They can control the malicious VMs that are running alongside the confidential VM. So for these attackers, like the attackers here, so this one, we say like they can intercept this memory bus like between the CPU and the memory, and then they can just dump the system memory out, and then they can also modify the system memory and to change these executions at runtime. And for the attacker here, like he can intercept or modify this IO traffic, and then they can also do this replay like attack on this IO traffic, and also it can access this shared memory, which is unencrypted, like to pass the data to these IO devices. Okay, so another one is say like you can control this malicious VM, and the malicious VM can run around if there is some like a side channel leakage, and then some malicious VMs can infer some information from the confidential VM. So this is a general like a threat landscape for confidential computing. So how does the like a confidential computing tries to prevent such attacks? So the first thing they will do is called like memory encryption. So the memory of this confidential VM is encrypted at runtime. And then the memory path between the CPU and the memory, system memory is also encrypted. So they will install like AES keys on the memory controller of the CPUs. Everything get out of the CPU will be encrypted. Everything read from the memory into the CPU will decrypted. So the CPU will execute this like a plain text instruction, but the memory will always be encrypted. And they also have this attestation path, means like for this CPUs, you can generate attestation report. It includes this measurement, like for this CPU's confidential computing, and then it's send this attestation report to the remote like attestation service, and the attestation service can verify whether it's a genuine like a CPU CC or not. And for the IO devices, as we talk about this data at rest and the data in transit, so they can use like these disk encryptions and the TLS to encrypt all the data, and then move it from the like the main private memory into this shared memory. So shared memory itself is not encrypted, but the data on it should be encrypted through the software. And then this IO device can read this encrypted data out of this shared memory and send it out to these devices. So this IO path between the disk and the shared memory is also encrypted. So the network card between the network card and the shared memory is also encrypted. And for GPU, it's a little bit different because GPU is kind of like a compute device. So instead of just to get some data and send it out, so the GPU will also do some computation on it. So for GPU, it will also get a data like from the shared memory. Let's say like if it's a CUDA kernel, right? It's a CUDA, you can encrypt this CUDA kernel. And then the GPU will grab this CUDA kernel like into the GPU's memory and run the CUDA kernel on the GPU's memory. And then you need to negotiate a key like between the confidential VM and there's like a GPU's confidential computing. And then unpack this CUDA kernel on your GPU's confidential computing to run it, right? And GPU confidential computing also has a GPU's attestation service. You can send this GPU's attestation report to NVIDIA, and NVIDIA can verify it. So whether all the firmware is up to date, and whether it's a genuine, like a genuine GPU or not, and then can provision, say, once they verified, and then they can be passed through to the confidential VM. Okay. Say when we talk about these security principles, in security research, we always talk about the confidentiality, like integrity and availability. We see like for confidential computing, it only protects these two, like the confidentiality and integrity of the memory, but it doesn't provide this availability because like these attackers can always do this denial of service attack, right? Because they control these compute resources. It can just cut this link like between the IO device and the confidential VM, or cut the link between the CPUs and the memory. So it can always do this denial of service attack. So availability is always out of scope from the confidential computing. Okay, so in the second part of this talk, I want to go through like this, what's applications for confidential computing. So I list the three here. So the first one is confidential containers. The second one is a confidential AI. And the third one is about this collaborative computing. So for confidential containers, so we see like for this confidential computing, we already talked about these benefits of confidential computing. So it can protect the confidentiality and integrity for the data in use, right? And then you can do this attestation, and you don't need to trust this computer like a provider. And the other like a benefit, so for the like in cloud, we always use this cloud native deployment, right? We use containers, we use like a Kubernetes, and then can deploy this your application very easily, like in the cloud. So for cloud native deployment, it has this portability like a benefit. It's like when you build your like a container image, you can just run anywhere, like in your cloud, and then you don't need to care about so what's a host OS is, right? You can just run your containers image. And also you can use a Kubernetes for scale out and to orchestrate the workloads, and then based on your demands. So if you have a high demand of request, and then you can just initiate like a more like a container pod and to handle this request. And also it is efficiency. It means like it can use this lightweight and can deploy the containers very fast, right? So these are the benefits for confidential computing and the cloud native deployment. So what do we see is how can we like combine these two and benefit from both worlds? And this is why they propose like the confidential containers. So confidential containers can leverage this confidential computing technology, like now they support like a TDX, SCV, and IBM SE and SGX. And also they also use a Kata container. So Kata container can wrap this containers or pod into a micro VM and then run this micro VMs with like a Kubernetes, right? So the simple solution is say like for Kata containers, they will use this micro VM. So if we use this VM-based confidential computing, we can just replace this micro VM with a confidential like a micro VM, right? And to run the pod and to run the containers inside this confidential VM to provide the protections of the confidential computing. So also they provide a technique called the secure image pooling. So traditionally for the cloud native deployment, they use a container D to pull the image, to pull the container image. But container D is running on the host. It is not running inside of the confidential VM. So you see the host is untrusted, like in the confidential computing's threat model. So they move this function from like a container D into the confidential VM. So they use a Kata agent inside of the confidential VMs to pull the image pull the image of the containers. Also, they have this built-in attestation, and they build a attestation system called a Trusty. And then the confidential containers can generate this attestation report for this micro VM and send to Trusty, and Trusty can provide once verified, it can provide a key, provision this key into the confidential VM. Okay. So the second application is about confidential AI. So we know like now everything is about AI. So when we want to run a like inference service, like fine tuning or training some models on some computers that doesn't belong to us, and then we can use the confidential computing to protect it, to provide this provide a secure environment for doing this like AI computation. So for this data, we see like the data like always contain this sensitive and private informations from the user. And for the model, it's like intellectual property. It's we spend a lot of money, like our computer resource to train a model. So it's very expensive. So we don't want to leak the data. We also don't want to leak the models to the untrusted like a computer provider. But maybe we don't have enough resources, but we have to use, say, cloud to do to launch this service. So how can we use a confidential computing to do that? And then so in this case, we can launch a confidential VM. And then we send this data in its encrypted form into the confidential VM. And we can also send this encrypted model into this confidential VM. And for this confidential VM, it can talk to a confidential computing's attestation service to say, to verify whether this confidential VM use a genuine CPU confidential computing and GPU confidential computing. And then it can also verify all this code, software running inside inside of the confidential VM, like this inference, like a framework, fine tuning, training software. They can verify the measurement of this like a software. So once they verify everything, and then this confidential computing attestation service can provide the key into this confidential VM. So they can use these keys to unpack this encrypted data and the encrypted model, and then load it into pipeline for this AI computation. So this is generally how they do this like a confidential AI using the confidential computing. And the third application is about collaborative computing. So this one, like we have multiple like participants. They have their own data, but they do not trust each other. So they don't want to share the data with each other. And what they can leverage confidential computing is say like in some like computers that doesn't belong to each other. They can just launch a confidential VM, and then they can do this attestation like with this confidential VM to see so whether this confidential VM is running on trusted hardware, whether it has its code like attested, and then they provide their private data to this confidential VM, right? And then once they get this attestation, report from the confidential VM, and then they use their own attestation service to verify it. Once they verify it, they can provide these keys for that encrypt this model or encrypt this data into the confidential VM. Then you can unpack this data, and for participant one, like they can also unpack this data into the confidential VM. And then you can use attested code to run against the data provided by both participants, right? And then once you generate this result, and you can share the result to different like participants. So one common case for it, okay, yeah.
Here, in your model here, you assume that each participant sending the data to you, and then you do the computation, right?
So you send something to environment that you can make a consensus, say this is a trusted environment, trusted by both parties. Yeah, you move the data into this trusted execution environment. And all the data, all the code inside it can be attested, meaning like you cannot load the malicious data into it. So if it's the malicious code inside this confidential VM, it can be detected by both parties. If they say it doesn't satisfy the security requirement, and then they will not provide the keys into this confidential VM.
So sometimes when, for example, when we have a visitor last week,
Mm-hmm.
when we talk in their context in health,
Mm-hmm.
when they say collaborative computing,
Yeah.
they're talking about the data is staying in my place. I'm not going to give you the data.
Yeah.
How do you apply this in that scenario?
Yeah, it's kind of like a federated learning,
Yeah,
right?
yes.
So in federated learning, you have this participant 1 and 0, they want to train a model together, but they will train the model in their local using their own like a GPUs to train a model.
Yeah.
And then they send it, so here it's not the data anymore, it's a model, encrypted model. So you send this encrypted model to the confidential VM, and then you can do the aggregation of this model. And then you pass the data, pass the model back to the participant, to share the model to the participants. Right?
Okay.
So they
this-
can collaborate with each other, but they don't need to share the data to each other. Right?
Oh,
Yeah. So this federated learning is a very representative, like a case for the collaborative learning.
Right, right.
Yeah, yeah. But collaborative can also, you can also pass the data into the confidential VM to the training data. Right? So it's a different ways of doing the collaborative learning. Yeah. Uh-huh. No, the inside of the confidential VM, when you're inside the confidential VM, when you retrieve the data, you retrieve from from CPU, right? So the key is on the memory controller of the CPU. So every time you read the data from encrypted memory, it will be decrypted on the CPU.
Let's say that. Using that now. So I'm process, so you environment, you CPU to the application, right?
Mhm.
But that's also stored, let's say, memory.
Mhm.
So is that getting from encryption on memory to decryption in the CPU to encryption again on the application, or the sending the application that's like decrypted?
So if it's loaded into the memory, it will be encrypted. And then when it's loaded into the CPU, it'll be decrypted. And then if you load it into another application, if the application is running inside the same confidential VM, it will use the same key to encrypt. So every data. So it'll be transparent. Like the key is always resident on the like the memory controller. So once you pass this memory controller, and then it will encrypt it. Yeah, so it's transparent to application. So from application's perspective, once it's like assembly code, like when they load this one into a register, right? So when you load some data from memory, and then it will, when you load it into CPU register, it will decrypt it, and then pass it into CPU register. Yeah. Okay, so we have talked about foundations and application. It seems like confidential computing is like a perfect like a technology, but in fact it has a lot of like limitations. And so in the third part, we will talk about this imperfect world. We'll talk about these system constraints and the security challenges of confidential computing, and how can we like tackle these problems in our own research. So for the modern like a confidential computing like a workloads, so I see like it needs this accelerator to offload to support this like parallel computing, right? You need the GPUs. And for SGX, it unable to offload the computation to accelerators. You need to run everything inside of the enclave. You cannot use the GPUs with SGX. So, and that's why they invent like the confidential computing on GPU, but for the generation on the Hopper, like they can only still do this software-based encryption and use a bounce buffer, because they need to like encrypt the data like into your shared memory, and then this the GPUs can read the data from the shared memory. So it will add another layer of like encryption like overhead to this communication between the CPU and the GPU. So we see like for the bottleneck of this training AI computation, most of the bottleneck is how to load the data from like your system memory into the GPU memory. And for the next generation of GPUs confidential computing on Blackwell, it still has this incomplete support for this trusted I/O. And as we know, like for the a software release for the NVIDIA driver, now they only support like bounce buffers on the on the confidential computings on the Blackwell. So it hasn't support like this trusted IO yet. And for the confidential computing workload, it also needed the support from software stack. As we talked like in SGX, you need to refactor your code to see which part is sensitive, and then you need to isolate the sensitive part into an enclave. It means you cannot just reuse your existing applications to run on SGX enclave, okay? And also they only provide a very limited SGX API interface. So all the like code need to comply with the APIs of SGX to run inside of the SGX enclave. So that's why SGX is not like that popular like recent days. Now they have this TDX and SCV, and TDX SCV, it's a VM based, so you don't need to change the code for your application, right? But you still need to change your code for the like a guest OS and host OS to support like support VM based confidential computing. And for the GPUs, the confidential computing, and you need to change your driver and to change all the like data transmission mechanisms between your GPU, like from your GPU, like a GPU driver into the GPU device. You need to change all the data paths. And then there's a lot of amount of like a legacy code and for you to change. And then there's a lot of vulnerabilities for changing like these like mechanisms for data paths. And also for the confidential computing require like this large memory capacity. Like for SGX, so initially it only support like 128 megabyte protected memory. That's a very small one, right? So if you want to run this AI model, you know, like the AI model is become bigger and bigger. You cannot just put like the whole like AI model into one SGX enclave, right? But in 2021, extended this ones to 1 TB, like, but it still cannot use like the accelerator on SGX. And for the GPUs, the confidential computing, so initially it doesn't have this multi GPU support. And so in the first release, you can only pass through like one confidential GPU to one confidential VM. And in the second release, they provided somewhat of a multi-GPU support on Hopper architecture, but they only provided this protection on the PCIe interface. So the NVLink between these multiple GPUs is still like unencrypted. And the NVLink encryption on the Blackwell is we still unknown. And so it may take years for us to see what happened on the NVLink like encryption. And we see like for this now, if we want to run this like a large language model, so one GPU has like 80 like a gigabyte of memory. That's not enough for the large language model. Usually like it take like 80 GPUs to run a big one, right? For the inference, for training, it may take a lot more like a GPUs. So it's still a long way to go. And here I list some like security challenges for confidential computing, but it depends on what's like your standpoint. So I list here is first one we want to talk about from the workload owners, like owner's view. Like we offload this computations to the untrusted cloud, and we want to protect this confidentiality and integrity of the data and the computation of my workload, right? So we want to see, so if the host is malicious, so can the malicious host like observe the data running inside of the confidential environment or not? Or if they cannot observe it directly, can they infer some information from it through some like side channels or not? And we'll also ask whether there's a malicious host can tamper with the execution integrity, like within the like a confidential computing. So whether they still leave some like a legacy like interface for use to tamper this like execution, okay? And we also see like a confidential computing add a lot of code changes to this legacy code. We'll see like whether these changes will lead to some like a vulnerability or not, okay? And in the worst case, if this confidential computing is breached, and how can we like minimize this like a damage? But we see a lot of research recent years to breach this like a confidential computing environment, especially on SGX and recently on SCV and the TDX. There's a lot of attack like in the security conference has been presented, okay? So the second view is on the accountability. This is from the compute like a provider's view. So as a, say, I'm a cloud provider. So if I allow you to run this confidential computing workload, and how can we know that you do not run some malicious workload in the confidential VM, right? So in my PhD, I do a lot of research on like a virtual machine introspection. So at that time, the virtual machine is kind of like a white box to us. We can see these bits and bytes in the memory, and we can reconstruct these data structures and monitor the execution inside of the virtual machine. But the confidential computing is contradictory to this capability, right? So it encrypts all the memory, and then you cannot do this monitoring from the like a hypervisor's perspective, right? And what if something is bad running inside of the confidential computing environment, right? So how can you prevent this one? And it also like in the collaborative computing, like if some like participants are malicious, if the participants like provision some like malicious data into a pipeline, and how can you detect whether some like a participant in the collaborative computing is malicious or not, right? So this is also a research question for accountability. If we know like someone is malicious, can we know like which one is malicious and who is responsible for this for the consequences? And third one is about like a transparency. So as a security researcher, so we want to know more about the system, but most of these implementations are proprietary, like a closed source. We do not know like how it's implemented. So and all these documents are mostly like for these end users, and it's not for like a security like researchers. So we want to know like how these systems are implemented. So here I will just briefly talk about our own research from like three like spaces. So first one is on the confidential AI. So we started this research very early, like in 2017, 18, and we are thinking about like how can we use the SGX for confidential AI, and especially for like a confidential inference and the confidential training. Okay. So left paper, this confidential inference via ternary model partitioning is a one for like a confidential inference using the SGX. So the research problem is simple. At that time, there's a lot of limitations for SGX, right? Enclave memory is too small, like 128 megabytes. You cannot load these large models into this enclave. And SGX cannot exploit these GPUs. And SGX, you need to like transform like this inference software stack to use SGX interface to run this inference. Okay, so these are the like limitations of the SGX, and what we tended to solve this problem is say like we do this model partitioning. So instead of just load the whole model into this enclave, we load part of it. But load part of it, the question is which part of it is sensitive, which part is not sensitive, and then we need some like a model assessment, like a framework to run this model and check its output to see so whether it still leaks some like sensitive information from this model or not. And then we can partition this model, say several layers, we can load it into the enclave, other layers we can just offload to the GPUs to run. And then it can do this to this assessment and the partitioning like automatically for like a different models. And then we use like a framework called like a darknet. Darknet is something that is in pure C. So then it's very easy for us like to transform this pure C-based inference framework to adapt it to like SGX. Okay, so in the second paper, so we want to talk about, so the research problem is say like a multiple participant, like they want to like train a model together, but some of them participants are malicious and they will try to like poison your data, poison your model. They will contribute some backdoor data set and then infuse it into your training. And then what you train the model has some backdoors in it, and then you will pass this backdoor models to like different participants. And for confidential computing, like it will hide this poisoning data from inspection. You cannot see so which data has contributed into the confidential like a computing environment, right? So this is a contradiction between this like a collaborative learning and confidential computing. So the key idea for this paper is say like instead of like record this raw data for all the data instances, so we record some like a fingerprints, a very small like a digest of this or representation of these data instances. And we also record who is the owner for these data instances, right? And then every fingerprint for all the training data has been recorded. And then at the runtime, so if we see if there's some like a misprediction happen at the runtime, and we check this mispredicted like inference data and to compare it with like the fingerprint data to see whether it's close in distance or not. So if a close one, and then we can know like who is who should be responsible for this like to contribute this like malicious data into the shared model. Okay. So the second line of work is we use a confidential computing for collaborative learning. So the first paper here is called like data. So like this one is about like a federated learning. So in federated learning, we see they will train the model in their local devices, and then we'll share this model updates to a central aggregator. But there's a lot of recent like attacks, say like if you get this model updates, and then you can reconstruct the training data from these model updates. So if some attacker like control this central aggregator, so they can just use this like a reverse engineering technique to reconstruct the training data. And then it will violate the security guarantees of federated learning, okay? And also for federated learning, they only have a central aggregator. So every like participant will send the model updates to the central aggregator. So if this central aggregator is breached, and then they will leak all the data to the attackers. So it will become a single like a point of failure. So we want to address like these two like problems for like a federated learning. So a straightforward solution for it is say like for the central aggregator, we're just running inside a confidential computing environment, right? And then you can provide this trustworthy like aggregation, and then you can verify the integrity of your central aggregator, and then you can encrypt your model updates to send to the central aggregator. But it doesn't solve the second question is this centralized aggregation still may be breached, like this CC may be broken, right? So what if some of the central aggregator is broken, right? So what do we developers say we call like a decentralized aggregation. So instead of just have one central aggregator, so we will have multiple aggregators. And each aggregator only have a small portion of this model updates. And also for the like the participant, they can partition their model, they can shuffle their models of parameters, and then send it to the aggregator. So for every aggregator, they can only see a fragmented and the shuffled like model parameters. So if one of them is breached, and then you can only leak a part of the data, and this part of the data cannot be used for this reconstruction attack. So that's why we call it like a federated learning with like a decentralized and like a trustworthy like aggregation. And on the right is a paper that we recently did this year. It's called like GPU traveling. It's based on the like the confidential computing on the H100 GPU. So the problem, as I mentioned for this, if it's a collaborative learning for like a federated learning, you need to exchange your parameters. Like you need to send your parameters to a central aggregator. But this model becomes larger and larger, right? There's a lot of like a performance cost to like a communication cost to send the model to the central aggregator. And every time they will do this iteratively. Every time they need to send this model. And if the model is too big, it will have a lot of cost. So the second one is GPU confidential computing has a lot of has a bottleneck. If you load this data from your CPU's memories to GPU's memory, it needs this software bounce buffer and to do the encryption. So this is a bottleneck for the GPU confidential computing. So what do we try to address this problem is saying we do not, so when we load the model into a GPU, we just let the model stay in the GPU. And then we let the GPU travel to different data holders to get the training data. So we just need to load the model once on the GPU and say this GPU can travel to the first data holder and to get some data to the training, and then go to the second data holder to do the training, third one. And then finally, they can have this a trained model on the GPU. And then this trained model can be shared by different data holders. So the key technique here is say we need to reroute these PCIe connections and to target a confidential VM. So it's kind of like a migration of these GPUs across different data holders. And then for confidential GPU, I'd add more a complexity into it because the confidential GPUs has its own context for the crypto, because you need to negotiate the keys with the confidential VMs to pass the data. So we also need to retain all these crypto and execution context for these GPUs when we travel the GPU around. Right? Okay, so the third line of this is about the security analysis for confidential computing. So we want to see whether it's secure or not. So in the first paper here, we investigated the problem in the confidential containers. So in the confidential, as we talked, it uses a Kata container, but a Kata container has a different threat model compared to confidential computing. So Kata container trusts the host control plane, trusts the Kubernetes, and trusts the container D, but the confidential computing doesn't trust anything on the host. So if you still use a Kata containers in confidential containers, and then these softwares on the host can still call these APIs to trigger these executions inside of the confidential VM. So then we consider these APIs are vulnerable, and these APIs can use to leak the data of this confidential micro VM, and it can also tamper the execution inside of the micro VM. So we do the assessment for this confidential containers API, and to see which part should be used by the owner and which part should be used by the host. And then for the owners APIs, we just have a secure alternative route for this for the owner to send a command directly into the confidential containers instead of using the host a control plane. And we also did 2 papers on the security analysis on Intel TDX system and NVIDIA GPU's confidential computing. So we consider it's, so now a lot of things are opaque, and we do not understand the internal, how inner workings of these systems. So that's why we try to use these 2 papers to explain to the people how it works, for TDX and for the NVIDIA GPU confidential computing. And for GPU confidential computing, especially we analyze all these data transmission mechanisms between the CPU and the GPU. And we find a lot of problems, weakness, because they use this legacy code, and they can still expose a lot of information on the shared memories to the attacker. So this is a reference for all these papers I just listed in the previous 3 slides. If you want to have a deep dive or to have a read on these papers, you can just check out. I think Shane will send these slides out to all the people here, right? And for the first 2 ones, it's on the SGX platform, and data is on the SCV, and Intel TDX demystified on the TDX platform. And the last paper, this one is on the confidential containers, and last 2 papers on the confidential computing on the GPUs. So that's all of my talk. And if you have any questions, just free to ask. Yeah. Mm-hmm.
But do you know whether or not they have a rotation mechanism?
It's a good question. You mean for the SGX or TDX or any other? Yeah, I know like for some of the, like as, I know for GPU confidential computing, they have this key rotation mechanism. So for a specific time after several iterations, they will need to like regenerate the key to protect the data paths between the CPU memory and the GPU. And for SGX and TDX or CV, I don't know that whether they have this rotation, but I guess they will have. But because if the key is leaked, and then it's doomed, right? So yeah, it's may have some like a rotation like a mechanism. Also, they say like if there are some like vulnerabilities in their firmware, you need to upgrade it, and then all the keys like embedded into your system will be like invalidated. Yeah.
They like based on yes, so I'm curious about like whether or not their focus on like you see what the post quantum photography stuff that in the works still just kind of based on.
I don't know that.
One question about the collaborative learning
Mhm.
practices there. You mentioned you have to, the data is stayed in the GPU and you can travel it.
Mhm.
Is the GPU still clocking like with active or it's like
Yeah, so
turning off?
yeah, in general, like say NVIDIA doesn't support that because they consider like if you have a confidential GPU, it can only pass through to one confidential VM. It does not allow you to so when you hot plug this GPU out, it should like scrub all the data on this GPU before it replug into another one, right? So that's why we had some like a hack on this part and say like when you like hot plug your GPUs to another like a confidential VM, because we retain this crypto like a context. So it is still considered this is the same like a confidential GPU because the new like CVM has like the key.
So basically, you touch the GPU with the VM.
And attach it to another one. Yeah. 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 You still keep the data inside the GPU. Yeah. If you do this reset, for normal like operation, if you do this reset, it will just clean up all the like GPU's data because it's for the safety reason, right? You don't want to leak your data from one CVM to another CVM. But if you say like these CVMs just collaborate each other, and then you don't want it to wipe out all the data on your GPU.
So another question is, I think one meeting published the side channel attack. I think at least for SGX, also side channel, even the meltdown spectrum also with SGX.
Yeah, yeah.
How about the situation VM based on GPU?
Yeah, VM based also has this side channel attack, like a spectrum meltdown. I think it also applies to VM based. Yeah.
That's not a major concern right now.
I think it's considered, say you can mitigate such attacks, right? But if there's a lot of new attacks every year, like on this trust execution environment.
Thank you all speak again. Thank you so much for what you provided here. Thank you.